Welcome to Electrodynamics. Now, what is electrodynamics? Electrodynamics is the study of electricity and magnetism and how they interact with each other. So, we'll be studying basically the interaction between magnets and electricity. Now, these forces play a huge role in our everyday lives, even though we might not notice them. So, they are there in our lights, fridges, and also uh, phones, the way we charge our phones. Now, when we dive into the realm of electrodynamics, we have things called AC generators and DC generators. So let's now focus on DC generators. A DC generator, which stands for direct current generator. So it's called a direct current generator because it only allows current to flow in one direction. This DC generator converts mechanical energy into electrical energy, and this is a real life example of a DC generator. Now, DC generators have their own advantages, one of them being they can provide a smooth output, which means they can provide a steady unidirectional current, which means they can provide a current that flows only in one direction, as I have stated before. Also, they are easy to control. We can easily control their speed and output power. The disadvantages of DC generators. So, the brushes and commutators can wear out over time, requiring regular maintenance, which means they can be quite costly. Complexity. They are generally more complex than AC generators. AC generators, we'll be talking about AC generators later in this video. And also the weight and size of DC generators tend to be bulkier than AC generators for equivalent power output. Now, DC generators uses Faraday's law of electromagnetic induction, the basis for how EMF is induced in a moving conductor within a magnetic field. So you might be wondering, what is EMF? Now, EMF stands for electromotive force. It is not a push or a pull force. It's not a gravitational pull like pushing on a wall. No, it is actually a potential energy that runs through the circuit. And this potential energy is provided by the batteries and also DC generators in general. They provide this potential energy to the circuit. And this EMF, it is measured in volts. So this is just a symbol for volts. It is just a V. So what you're looking at is a representation of a DC generator. So it is made up of the south part of the magnet and the north part of the magnet. So when you look at these blue arrows right here, these blue arrows, they show us the direction of current. Remember, we said that DC generators only allow current to flow only in one direction. So current flow through this coil in that direction. It goes around and comes back around. What goes around comes. Okay, never mind. Okay, next up we have something called a commutator. So we have this thing, this round thing here, this circular thing over here is called a commutator. That is a commutator. Or you can also call it a split ring. Now, a split ring is another way it's another way we can use to differentiate between a DC generator and an AC generator. AC generators do not have a split ring. Only DC generators have split rings, and we call it a split ring because of that gap over there. If you look close, there's a gap there. There's a gap. So if you don't see a gap, that is not a DC generator. So what is a commutator or a split ring? So a commutator is a device attached to the coil and only allows current to flow in one direction. So the purpose of this split ring is to allow current to flow only in one direction. That is why we said DC generators only allows current to flow in one direction. It is because of this split ring. Okay, now attached to the split ring, we have something. Do you see those black things over there? So they are called brushes. They are called brushes. Now, what do brushes do? So the brushes connect that coil over there, to the external circuit. So when you look here, this is the external circuit. So the brushes allow the current to flow to this circuit over here. And those lines, the red lines, they show magnetic field. They show the direction of magnetic field. The direction of magnetic field flows from north to south. Now here's another presentation of a DC generator. Try to label the diagram based off what we have learned so far. Take a few seconds, pause the video and label the diagram. Welcome back. Now, when I look at this diagram, the first thing that I see is a ring. I see this ring and I see a gap there. When I see a gap on a ring, I know it's a DC generator. So now that ring is a split ring because there's a gap. So we have a split ring or a commutator. Now, I also see these little red things here and they are attached to the split ring. Those are brushes. And also, this is current flowing in one direction. And we'll also have the north part of the magnet and the south part of the magnet and the magnetic fields, the magnetic field lines. Now, do you remember where the direction of the magnetic field? Do you remember? It goes from north, it flows from north to south. So if you look here, we have another presentation of a DC generator and we have that commutator or a split ring. We also have the brushes which connect the internal circuit to an external circuit. In other words, they connect the coil to the external circuit, in this case, which is the bulb. Here's a graph of a current in a DC generator versus time. So when you look at this graph, the current is only going up and down to zero, and then going back to maximum, going back to zero, and so on. It does not go below the x-axis. It only goes to the max and back to zero, max, zero, because it is in one direction. Now let's say we have two magnets, the south pole being on the left hand side and then the north pole being on the right. So notice that the magnetic field always flows from north to south. So I'm trying to explain to you how did we get this graph. So if we have a coil and that coil is perpendicular to the magnetic field, just know that the current will be at zero. That is why we have our graph starting at zero. And whenever the graph is at zero, whenever the current is zero, the coil is perpendicular to the magnetic field. Now, when we have maximum current, when the current is at those peaks, those four peaks, the current is at maximum and it indicates that the coil is parallel to the magnetic field. Now let's talk about AC generators. So you've probably seen one of these before, and also this is a AC generator, and that is just another picture. You can just ignore that. So AC stands for alternating current, which means that the current usually travels back and forth periodically. So it also converts mechanical energy into electrical energy. So this is a presentation of an AC generator. So it also has the north part of the magnet and also the south part of the magnet and a coil, but it does not have split rings, but it has slip rings, and it's also connected to the external circuit, and those are the brushes. And this is how a split ring looks like. It has it has no gaps in between. It's just a ring. This is how it usually looks like. So AC generators also use Faraday's law of electromagnetic induction. So according to Faraday's law, when a conductor moves within a magnetic field, an electromotive force is induced in the conductor. So this is how the current versus time graph of an AC generator looks like. So it's basically a sine graph, a sinusoidal function. So the advantages of AC generators. So transmission over long distances. AC generators can be transmitted over long distances with minimum energy loss, using transformers to step up or step down voltage. So they are reduced in maintenance, unlike DC generators. AC generators do not have commutators or brushes, reducing the need for maintenance. So now coming to the disadvantages of DC generators is they are very complex. the design of AC generators and the systems required to convert and regulate AC can be very complex. And safety, they have high voltage, so they are not that safe to play around with. So here's a diagram. Is this a DC or an AC generator? So the first thing that we look at is the ring. So we have a ring there, a commutator. So that ring or commutator has a gap in between, a gap there and a gap there. So this is a DC generator. Now here's another question. What is the purpose of the commutator for the generator you chose above? So remember that the purpose of a split ring in a DC generator is to allow current to flow in one direction. Let's say current is flowing through this direction in this coil, so it will flow in that direction, and this is because of this split ring. So the purpose of this commutator or a split ring is to allow current to flow in one direction. Here's another question. Name the principle on which the machine operates. Can you pause the video and try to remember what we have discussed in the previous slides? Welcome back. So your answer should be electromagnetic induction. Remember we said that a DC generator uses the principle of electromagnetic induction. So your answer here should be electromagnetic induction. Now here's another question. State one way in which the bulb can burn brighter. Remember the bulb is being connected to that coil through those brushes, so the bulb is an example of an external circuit. So how can we make the bulb to shine bright? So how can we do this? So there are several ways. The first one is to increase the number of coils. So here, let's say we have one coil. So this is just a coil. So when we increase the number of coils there, let me use another thing. So let's say we have another coil here, coil, and they are connected to this commutator. We have a lot of coils there. The bulb, the current will be higher, and then the bulb will burn brighter. So one of the answers is increase the number of coils. So I do encourage that you take notes, because this is very important and we haven't discussed it previously, so we are discussing it now. So this is one of the ways in which we can make the bulb to burn brighter. So another way to make the bulb burn brighter is to rotate that coil faster. So let me use, okay. So when we rotate this coil faster, when we have a faster rotation, the bulb will burn brighter. So we have rotate the coil faster. We also have another way in which we can make the bulb to burn brighter, which is increase the strength of magnetic field. So these magnets should be stronger. When we use stronger magnets, we will have a stronger magnetic field, therefore increasing the current that runs through that coil. Then the bulb will burn brighter. So another way to make that bulb to burn brighter is to use strong magnet, or you can say increase the strength of magnetic field. Remember, the magnetic field is related to magnets. So when we have a stronger magnetic field, the stronger the magnet. Here's another diagram. So can you tell if this is a DC or an AC generator? Pause the video and take your time. So when we look at this diagram, we have two rings. We have two rings, but we must consider something. When we look at these two rings, they do not have a gap in between. They do not have small gaps on them. They are not cut. So these are not split rings, obviously, because they don't have a gap. They are not cut. They are not split rings. These are slip rings. So this is not a DC generator. This is an AC generator. Now let's leave. Okay, I've already told you, but can you guess what that X is? I've already said it. That is a slip ring, not a split ring. They do not have a gap. So here's a cross section of how a slip ring looks like. So a slip ring looks like this. It's been cut into half. That is a split ring. And then a slip ring, it is just a ring. So when you see a slip ring, that is an AC generator. And also, as you can see, the brushes are connected to an external circuit, which is the bulb. Now here's another question for you. We have a graph here, which is the EMF against time. So now, does this graph represent an AC or DC generator? Take your time, pause the video and think it through. Welcome back. So remember we said that a DC generator goes from 0 to maximum and then back to 0, then to maximum. So we have something like this for a DC. So for DC, we have something like this from 0. Let's say we have a graph here. So it goes from 0, max, 0, max, 0, max, 0, max. So a DC just goes from, it's direct, it just goes 0, max, 0, max, 0, max. But this one does not go 0, max, 0, max. It goes from 0, max, 0, negative max, 0, positive max, 0, negative max. So this is a sine graph, and this represents a AC generator. So well done if you got that. So this is just the sinusoidal function. And also remember, it cannot always start from 0. A sine graph also can start from here sometimes, It can start from here. Let's say here it's T0, so it can start from here and goes down like that, depending on the type of question they'll be asking you. So yeah, it can start from here or here, or it can also start from here at T0, starting from here to there. So here's another question. Define the term root mean square value of an AC voltage. So I do encourage that you take notes here, because we haven't went through this on our previous slides. So just be active. So here we have a root mean square. So a root mean square is a value for voltage. So, and it is usually represented as Vrms. It's the value of a voltage. So how do we define this? So the root mean square of an AC voltage, it is the value of voltage of a DC generator that will have the same heating effect on an AC generator. So a Vrms value of an AC voltage, it is the value of voltage of a DC generator. So this is the value of a DC generator, the value that is found from a DC generator, and this value will have the same heating effect on an AC generator. Let me simplify this for you. So think of Vrms like the strength of waves at the beach. Sometimes the waves are big, so sometimes the waves are big, so sometimes we have like bigger waves at the beach, and then sometimes the waves are very small, something like that at the beach. Now when somebody asks you how strong are the waves at the beach, let's say maybe the beach at California, whatever, wherever, so Mauritius, wherever, we might talk of average height, the average height of the waves. We might speak of the average height of this wave, which might be a little bit around there. So we have the height of that big wave, and then we have the height of the small wave. So let's say that is 40, and then here we have 20, so that might be a little bit around 30. So this is the average height of the waves at the beach. So we might talk of their average height when someone asks us how powerful are the waves at the beach. So similarly, Vrms is like we are talking about the average height of the electricity waves in your house. It helps us understand how strong the electricity is on average, even though it's always changing. Remember, the voltage of AC and DC, it's always changing, but we can talk of the average between the voltage of AC and DC. That is Vrms. It's like the average voltage between AC and DC. Here's another question. It says calculate the RMS voltage. So the RMS voltage, it's Vrms. And this has a formula. So the formula for Vrms is equal to V maximum divided by the square root of 2. So when we look at this graph here, this is for the AC generator. So when we look at this graph, where is the maximum voltage? The maximum voltage will be at the peaks there. Not there. This is not the maximum. The maximum voltage will be there. So we have those peaks over there, and the maximum voltage is 339.45. So to find the Vrms voltage, Vrms is equal to that value over there, 339.45 divided by the square root of 2. Now you can put that into your calculator. So we have 339.45 divided by the square root of 2. This will give you a value of 240.02 volts. Remember, it's still voltage, so it is still in volts. And make sure your calculator is on degrees, not radians. Here's another question. So we have a graph there. So what does this graph represent? Which generator does this graph represent? Pause the video, take your time, and just figure it out. Welcome back. So when I'm looking at this graph, I have a sine graph. So it goes up, down, going negative, going back to 0, going up, and like that. So we have a sine graph. And what do I remember about a sine graph? It's AC generator, alternating current. So we have an AC generator here. Now let's try to find the Vrms, the root mean square voltage for this AC generator. Pause the video and try it yourself. Welcome back. So remember, the Vrms, the equation for the Vrms is equal to Vmax divided by the square root of 2. Now, where is the Vmax when we are looking at this graph? So that will be 340. So this will be 340 divided by the square root of 2. You can just plug that into your calculator, and this gives you the root mean square of 240.42 volts. So now let's say we have an AC generator. So we have an AC generator, and this AC generator, it is connected to a light bulb. So this AC generator has been connected to an external circuit, which is a light bulb, and we are being told that this light bulb has the power of, let's say, 150 watts, and it glows at maximum brightness. So it is glowing at its maximum brightness. Now the question says, find the resistance of this bulb. So I do encourage that you take notes here, since we haven't discussed this previously. So we have several equations in which we can do this. The first one is to find the average power. So the formula for average power is P average is equal to V RMS squared divided by the resistance. So what we are looking for is the resistance. To find just the resistance, that's what we're looking for. And we have already found our VRMS previously. There's it, which is 240.42. So what we can do now is to plug the values that we have, and also we have power. Our power is 150 watts. So power is being measured in watts. So we take this power and put it there. So we have 150 is equal to VRMS, which is 240.42 squared divided by the resistance. But we are looking for the resistance, and how can we get that resistance? We can multiply both sides by R, and when we multiply both sides by R, let me do this, multiply this side by R, multiply this side by R, and when I multiply this side by R, that R will cancel out with this R, and then we'll be left with 1 here, and then 240.42 squared divided by 1 is 240.42 squared. So we are left with 240.42 squared. Now we are still looking for R, the resistance. What can we do from here? We just divide both sides by 150. So this side we just got rid of 150 is out, and then the resistance R is equal to, just plug that into your calculator. We have the resistance of 385.3 ohms. The resistance is being calculated in ohms. Sorry for the background noise. So let's say the question says calculate the RMS current. So the RMS current is usually represented by IRMS. So to find IRMS, we can use several equations as well. So another way we can find that is to say it's like this. The average power is equal to IRMS, multiply that by VRMS. So we already have the average power, which we got from the previous question. So we have 150 watts. We can just plug that in. So we have 150, and then we have the VRMS, which is 240.42 volts. So we have IRMS here, multiply that by 240.42 volts. So we are just looking for IRMS. So what we can do is to divide both sides by 240.42, 240.42. So that goes out, and your answer should be 150 divided by 240.42, and that should give you something like 0.624 amperes. So current is measured in amperes. Now there is another way in which we can find IRMS. So we can just do this. So another way in which we can find IRMS is by using Ohm's law. Remember that I usually write this everywhere, like before I attempt questions, especially electric circuits. I usually attempt this. So I usually write this down, V. So this is Ohm's law. So to find this is I. So to find the current is equal to voltage divided by resistance. So, but we are looking for IRMS. So we can just do this, replace that with IRMS and VRMS. The resistance is just the resistance. So previously we found the VRMS, which is 240.42. So IRMS is equal to 240. No. Okay, yeah. So I usually write this everywhere when I attempt electric circuits questions. So we have V, R, and I. This is Ohm's law. So when we look at this, when we are looking for I, so I is equal to voltage divided by resistance. So we have V over R. So, but we're looking for IRMS. So IRMS, V RMS. So we can just replace that with RMS and RMS there, and resistance just stays the same. So we're looking for IRMS. We need VRMS and the resistance. So previously we have found the VRMS, which is 240.42. So we have IRMS is equal to 240.42 divided by the resistance. We have found the resistance previously, which is 385.3. So we have 385.3. So you can just plug that into your calculator. So that is, there's 0 there. And IRMS is 0.624 amperes. So we still get the same answer. So what I would recommend is to always find the VRMS, which is the maximum voltage divided by the square root of 2. And after that, you can write all of these equations down if you're not given them, and they will help you to find other stuff.